So, welcome everyone to this Eusipco 2024 3MT competition. So, just take a seat and we will be together for roughly 1 hour. So, first of all, we need to thank all the PhD students who prepared very nice videos about their PhD subject. And we really wanted to emphasize that we learned a lot because the scientific presentations was very good and the pedagogical efforts were very appreciated. The choices were very difficult to make, so we need a special thanks to the devoted jury that helped us. And this, so this event in Eusipco 2024 is a Eurasip action. So we need to thank both the Eusipco 2024 committee and the Eurasip board for their trust. Thank you very much. And a special thanks to Nelly Pustelnik, Director of Technical Program and Membership, for our support during the entire process. So a few figures and information about this competition. We were really happy to receive applications from all over Europe, from Portugal to Finland, and from Romania to Scotland. Yes, this is Europe. But also from Asia, from West Asia, Israel, to East Asia in Malaysia. And this morning, the General Chair said that Africa should be better represented in a Eusipco event. And our first finalist is from Morocco. So tonight, you will have two missions. First, you will need to enjoy this event with us. And second, you will have to vote. Because at the end of this session, 3 audience prizes will be awarded. So these prizes are sponsored by Elsevier, so thank you very much to this editor for sponsoring the event. And this is also sponsored by the audience of Eusipco 2024. So I clearly emphasize that you have an important mission tonight, and the General Chair recalled you that 3MT is about science, so you will have to evaluate our 10 brilliant finalists based on their ability to provide a clear, original scientific message through a lively and enthusiastic presentation. So please, when you will listen to them very carefully, have in mind that science is about everything in Eusipco. So you received some voting sheets from our devoted volunteers and pens to just give some points to your opinion, the best 3MT presentations. So you won't have to rank the presentations. You have 3 points to give to 3 finalists, and you just put a cross in the corresponding case on your voting sheet. So maybe a very quick reminder of the rules and how a 3MT competition is run. So the finalists will have exactly 3 minutes to make their presentation. You have here a timer, and they also have a timer on stage so that we can stick to this schedule. It's not permitted to dance, to rap, or to bring extra material, so it's all about your human presence and your scientific message. And so this is all for Julian and I, and we will let the stage to our finalists. I propose that we applaud them before, because they did a good job. And so our first candidate is William Marnissi. So, thank you very much.
Picture this. You have this very important meeting you need to attend. You enter your car, it is rush hour, almost impossible to make it in time. So you think of Waze application that gives the best route to avoid traffic jam and therefore reach your destination at optimal duration. But how does it work? In a nutshell, machine learning. In fact, machine learning algorithms have been widely used to exploit the data of IoT devices without any human intervention in order to make fast and real-time decisions to improve humans' lives in many fields. In our example, that would be considerably reducing traffic congestion. Now, most of the existing machine learning techniques assume that all data is shared with a central server, which obviously violates users' privacy. And here is where federated learning comes in the picture. The main idea is that each device trains locally its machine learning model and only sends the machine learning parameters to a distant server. So no personal data is shared and privacy is preserved. However, federated learning poses several challenges as the limited wireless resources combined with the heterogeneous property of the devices lead to a significant energy consumption and a large latency, which is impractical in real-life situations. As a PhD student, my research focuses on resource optimization for an efficient federated learning. I study the parameters that have an impact on time and energy needed for conversions, and I propose mathematical algorithms to optimize them. To address the heterogeneity challenge in federated learning, I investigate client sampling techniques. As an example, to respect the resource constraints while accelerating the conversions, I propose to select at each communication round the optimal subset of devices based on their gradient norms. However, federated learning involves sharing high-dimensional updates frequently between these selected devices and the server, which is challenging in limited resources scenarios. As a solution, I propose that instead of conveying the whole updates with full 32 bits precision, we send only a part of it. It's called sparsification. With limited bits precision, it's called quantization. To achieve this, I formulate an optimization problem that chooses the best sparsification and quantization levels at each round in order to minimize the overall energy while meeting the target accuracy and respecting the time constraints. Thanks to its privacy-preserving property, federated learning is applied in different contexts: healthcare, autonomous driving, agriculture. I hope my research contributes in advancing the efficiency of federated learning algorithms and therefore to actively be part of the AI revolution. Thank you.
Thank you very much. Our second participant is Eric Wang. Please come to stage.
Okay, good evening, everyone. Have you ever tried using voice typing or a voice assistant like Siri in a noisy place, such as a bustling cafe or at a concert? It must be really frustrating when your device keeps getting it wrong, right? This common problem shows why we need to improve the noise robustness of automatic speech recognition, or ASR. My PhD research aims to achieve this by using powerful speech enhancement, or SE, as the front end of the ASR. SE can remove noise from speech before it reaches the ASR system. So this idea sounds reasonable, right? But in fact, directly combining SE with ASR can be a disaster. Why? Because SE and ASR models are often trained separately, and SE can create artifacts during denoising, which can confuse ASR even more than noise itself. To better understand this, we can think of SE as a razor. If you don't shave properly, then you'll cut yourself and leave some scars and make you look worse without even more than without shaving. But unless you're Brad Pitt or yeah, anyway. So common solutions for the SE artifacts includes fine-tuning or training SE and ASR models together. But these methods are often expensive and even impractical for commercial models that are not accessible. So our solution is to develop post-processing modules to efficiently bridge the gap between SE and ASR. Specifically, we've designed lightweight neural network model to decide how much we mix the noisy and enhanced speech, so that we can balance noise reduction with artifact prevention. One simple way to achieve this is by estimating the signal quality of the input speech. If the signal quality is high, then we rely less on SE to prevent artifacts. Conversely, if the signal quality is low, then we rely more on SE to remove the severe noise contamination. Other techniques like reinforcement learning can also be helpful for developing the bridge module. By receiving feedback from the ASR, our module can learn to decide the best mix of the noisy and enhanced speech so that we can achieve ASR's performance. All in all, our module can efficiently integrate various SE and ASR systems, making it more reliable in noisy environments. Imagine a world where your voice can control a device smoothly, even in noisy places. How convenient would that be, right? This is the future I'm working towards. Thank you.
So we will now listen to Renke Wang.
So, since the advent of Nyquist-Shannon theorem, sampling has been crucial in digital signal processing. However, 75 years later, this is not enough. New sensing and imaging techniques call for novel sampling methods to ensure a faithful reconstruction from these new data acquisition models. This concern is especially critical in the micro world. For example, estimating accurately viral structure is crucial for vaccine development. For this purpose, the most recent imaging technique is called cryogenic electron microscopy, also known as cryo-EM. In cryo-EM, to estimate 3D structures, molecules are rapidly frozen in a thin layer of ice. An electron beam then passes through, forming their 2D tomographic projections on a detection plane. Since molecule orientations can't be controlled, the projection measurements are actually taken at different unknown angles. Although this problem has been studied for practical implementations, there are still open questions regarding the uniqueness of the solution and the existence of algorithms to recover exactly the 3D signal. So to theoretically understand the process, we consider the problem from a sampling perspective by modeling the point spread function of the lens as a sampling kernel and the sensor grid as a sampling grid. So the fundamental question is, under what conditions can the original 3D signal be perfectly reconstructed from its filtered and sampled 2D projections at unknown angles, and what is the minimum number of projections needed to achieve this? To obtain uniqueness conditions, we consider the 3D signal to be polyhedron shapes. Then by leveraging divergence theorem, we show that at any projection angles, 3D geometrical features can be extracted from these discrete 2D samples. Moreover, for any polyhedron shapes, given as few as 3 projections, the original polyhedron and projection angles can be estimated exactly by applying an algebraic approach on the extracted features. We further propose a robust algorithm which tackles severe measurement noise and allows arbitrary sampling kernels. For the first time, we present a theoretical analysis and sampling method for the unknown angle tomographic reconstruction problem. But this is just the start. We have evidence that this can be applied for more general shapes. Moreover, we have collaborated with Rijksmuseum Amsterdam to visualize the internal structure of museum objects. Due to the lack of affordable city equipment and the challenge of transporting precious objects, 3D imaging in many museums is hard using only basic X-ray equipment. With our proposed method, we can calibrate the imaging system and yield accurate 3D imaging without the need of costly city systems, which shows the huge implication of this method. Thank you.
Our fourth participant is Antonio Giganti.
As we all know, climate change is one of the most significant challenges facing the world today. And with my research, I propose to produce an enhanced version of gas emission maps. I'm going to focus on the biogenic volatile organic compounds, well known as BVOC, which are gases produced and released in the atmosphere by plants. BVOCs are needed in multiple plants' life stages, such as growth, development, reproduction, and defense. And they also serve as a medium for plant-to-plant and plant-to-insect communication as well. So, until now, everything seems to be fine. But what would you think if I told you that these gases could seriously harm humans and the environment? The problem is not on the plant side, but it is related to the contrasting role that these gases have in the biosphere-atmosphere interaction. Of course, we all know that vegetation is a dominant sink for atmospheric CO2. However, BVOCs have a negative impact on the atmospheric chemistry because they promote the formation of pollutants and affects the residence time of other greenhouse gases that we all know to be detrimental to human health. For these reasons, providing biogenic inventories with a more detailed spatial resolution and temporal evolution could help policymakers in develop better strategies and regulation to combat the climate change. At first sight, our problem could be seen as a classical image and video enhancement. However, this is not. We need to build algorithms that are physically aware of the generation and the evolution processes of these gases. And in this way, producing more detailed biogenic emission maps could help many industries in making more informed decisions about their activities. For example, farmers might reduce the amount of fertilizer and pesticide used and also improving crop yields. Also in forestry, where better management practices could be developed to reduce the environmental impact of logging activities. And also in urban planning, where a very detailed biogenic emission map could help the design of green spaces to reduce the environmental effects of harmful emission and promotes the livability of the cities. And I think that this is a crucial step towards a more sustainable and a good future for us and the next generation. Thank you for your attention.
So we will now listen to Maria Saranour Sadoun.
What is the common factor between taking a coding interview, running to not miss your conference flight, or just standing in front of a whole auditorium? It's stress. It orchestrates our life in modern society, which drains us of a much-needed energy, but also poses a major threat on both mental and physical well-being. This reality ignited exciting research synergy around human-machine interfaces for stress management using biofeedback or non-invasive stimulation. However, this requires first quantifying stress, a very challenging task, given the inherent physiological complexity and several technical challenges. Because while subjective assessment is not reflective of physiological reality, existing methodologies also may be satisfactory. In my PhD thesis, we aim to assess stress based on multimodal cortico-cardiovascular recording with the ultimate goal of identifying bioindicators during cognitive and physical stress. For that, we propose a framework that combines both signal-based and model-based methods that complement each other. How so? Well, signal-based method extracts subject-specific information that dynamical models need to infer inaccessible variables, therefore enhancing inter- and intra-subject generability and interpretability using less data. Our project is divided in two main axes. The first focuses on creating a database unique in the state-of-the-art of simultaneous synchronized recording of EEG, ECG, and continuous arterial blood pressure signals during cognitive and physical stressors. To unfold our reasoning on the second axis, the dynamical model of stress models a perturbation of emotional equilibrium based on autonomic cardiac regulation. However, the link between cortical and cardiovascular responses to stress is pretty unclear. We address this by exploring the dynamical modeling of brain-heart interaction link in both. Next, we approach the challenge of estimating the model's parameters that are time variant and subject-specific through a feature engineering part that captured the nonlinearity and chaoticity in the dynamics and morphology of the signal, using method based on the Schrödinger operator and graph theory. These features are then fed in a deep neural network that estimate these parameters. Next, estimation tools as observers infer the model state, and a feedback loop corrects the training. The output being the central blood pressure, the heart rate, along with the coefficient of bidirectional interactions, are all leveraged in elaborating indicators of stress and metrics with the input of experts in physiology and neuroscience. As an end note, while we aim to build personalized, robust tools to decode our responses to stress, and we all have to keep in mind that the scientific progress we are dedicated to aims and have to help the most disadvantaged of us, including me and all of us. Thank you.
Our sixth participant is Daniel Kraus.
Imagine you're walking in a busy city street. On the left side, you hear some cars honking. On the right side, you hear pedestrians walking and talking with each other. This process is something that we call acoustic scene analysis, and it consists of many different audio tasks, such as sound event detection, sound source localization, and acoustic scene classification. Those skills are something that we as humans take for granted, but what do we do to teach machines to do those exact things? Well, that's something where binaural audio might come in handy. Binaural audio is something that we obtain by putting microphones in our ears and recording all the sounds that happen around us. This way we are able to obtain recordings which resemble the real human perspective. And by using that perspective, we can create and enhance technologies applicable across many different domains. Millions of hearing-impaired people might benefit from hearing aids that use acoustic scene analysis systems in order to enhance the understanding of speech, even in noisy environments. Surveillance systems might use detection and localization systems in order to detect hazardous events and raise an alarm immediately. And finally, robotics. We've probably all heard people that say that we don't want AI to do our art and writing, we want AI to do our laundry and dishes. Well, if we want robots to perform our daily tasks, we first need them to understand our human environment, and that includes the acoustic content as well. In my research, I develop deep neural networks and study different acoustic recording scenarios, including the involvement of a rotating head and a listener moving freely in space, in order to merge the benefits of binaural audio and acoustic scene analysis to create efficient solutions applicable in all the aforementioned fields, to improve human health, to improve the safety of our daily lives, and to automate tasks that we don't want to do ourselves. And yes, that includes your laundry and dishes as well. Thank you.
So the next speaker is Annika Bregleb. And before Annika presents, I want to remind you that a static slide is permitted, but not mandatory. So there is no bug if there is no slide. It's just that you will have a purely human presentation.
What is signal processing in the AI era? This question has been driving the signal processing community for quite some time now. Even from looking at the technical program of Eusipco, it is clear that data-driven machine learning techniques are an important part of signal processing research. But still, the audio signal processing community, for example, has spent decades on tackling tasks like denoising or target speaker extraction with model-based approaches. Should these models be discarded just because data-driven black box approaches don't seem to require them anymore? Of course not. But can we connect these models to neural network architectures with hundreds of thousands of parameters? Most explainable AI approaches these days provide example-based explanations of which input features have the most impact on the predicted output. While this is useful, it does not really explain the signal processing happening inside the neural network. So, looking at the problem of multi-channel speech enhancement, I attempt a peek into the black box. In multi-channel speech enhancement, we typically differentiate between spatial and spectral processing. But do end-to-end neural networks actually use spatial information? To answer this question, I proposed a set of analysis tools that allow to identify spatial and spectral information represented inside the neural network. By using simple techniques like k-means clustering, and by designing specific test scenarios, we can pinpoint parts of the neural network that are responsible for spatial and spectral filtering. We find that memory elements, such as LSTM or GRU layers, are crucial for spatial filtering, where signal phase alignment is an important processing step. We also find that the type of target signal used for training the neural network has a strong influence on the spatial filtering capabilities. In addition, we observe that building blocks intended to provide a certain functionality sometimes do not work as expected. However, based on the analysis, we can propose adaptations to provide these functionalities. In conclusion, using specifically designed analysis tools, it is possible to identify processing steps from conventional signal processing in neural networks for speech enhancement. In addition, we can propose modifications to existing neural network architectures to improve performance, adapt them to a new task, or at least increase the interpretability of the signal processing pipeline, turning the black box a little bit more transparent. Thank you.
Our next speaker is Thomas Depiche.
During the COVID-19 pandemic, we all had to reduce social contacts as much as possible to slow down the spread of the virus. Work life as well as social life was often moved to online media, most importantly to video calls, and while in the beginning this was often seen as a welcome opportunity, after a while people got fed up with endless video calls culminating in the term Zoom fatigue. But on the other hand, we have to see the huge opportunity that remote communication gave us in reducing travel and connected CO2 emissions. In April 2020, for example, we saw reduced commercial flight activity of almost 75%. In my PhD, I work on making remote communication more natural, which may help making remote meetings more attractive. To achieve this, I developed signal processing methods that preserve all the cues that make speech appear natural in our real-life environments. Spatial cues, for example, help us to localize sound sources and to concentrate on individual sounds in a mixture. This is also known as the cocktail party effect. Another key component is to understand and to add the acoustic properties of the near-end environment and to add them to the remote speech to make it blend into the near-end environment. This helps to reduce the so-called room divergence effect, which sometimes reduces our ability to perceive headphone-rendered sound sources as being located outside of our head. More specifically, I work with microphone arrays that are sometimes located on a user's head. These microphone arrays are getting more and more common as they are getting integrated into augmented reality headsets or smart glasses. In my signal processing algorithms, I model the influence of the microphone array on the speech signals and estimate spatial room transfer functions of the environment. In the estimation process, I use de-reverberation and beamforming to estimate a reference signal, which I can then relate to the array signals to estimate the spatial room transfer function. In more realistic cases, this can get, however, a bit difficult, as the microphone array may rotate and move through space as it's on the user's head. I found that by estimating sound field coefficients in a continuous space domain, as for example expressed via spherical or circular harmonic basis functions, I can update the room transfer function estimates during arbitrary array rotations. In future, this should also be extended to support movement of the array, but some first results I can show on Thursday during this conference. Thank you.
We will now listen to Sonal Baberwal.
Hello. Recently, we have been hearing about brain-computer interface systems, or BCIs, to use our thoughts to control devices. Imagine thinking about a movement and using this thought to control an exoskeleton or a robot or screens or cursors. Motor imagery is imagination of a movement without performing a movement, and this has similar brain signals to actual movement. My PhD revolves around motor imagery-based BCI systems. In this system, a user wears an EEG cap, which acquires the brain signals, which are then translated into actionable commands. For instance, when a person imagines left or a right-hand movement, features are being extracted from the amplitude of the brain signals, which are then classified into left or right-hand movement to operate a device. This technology is used to assist people suffering from spinal cord injury or neuromuscular disorders or stroke rehabilitation. Despite the research being conducted for decades, this technology is not outside laboratories yet. My goal is to bring this technology outside laboratory by working at every stage of the system. Initially, training plays a significant role in motor imagery-based BCI systems. I hypothesized whether the training medium could enhance the brain signals. A user study was conducted using 21 participants where I realized that the users perform best when the training was conducted into VR medium. Another avenue is to optimize the entire system and reduce the complexity by bringing the entire system into a single channel system. This was done by combining Fisher's ratio and Pearson's correlation to perform a single channel-based classification for motor imagery. One last possibility is to have safe interfaces when we think about activities of daily life. Here is an example of pressing a spray button from your imagined thoughts with a soft robot. By combining all these efforts, I aspire to bring this technology outside the laboratories to assist people suffering from spinal cord injury, neuromuscular disorders, stroke rehabilitation, and bring a real change for enhancing human performance. Thank you so much.
And we get to our final speaker, Thibaut de Surel.
As we have just heard, brain-computer interfaces can sound exciting and like science fiction. Imagine a world where thoughts become commands, where a paraplegic person could control his prosthetics only using its brain. This is the world that could be made possible using brain-computer interfaces, or BCIs. And this, only using a dozen of sensors equipped on the scalp of the subject that each record the electrical activity of a certain area of the brain using electroencephalographies, or EEGs. Then, those EEGs could be translated into real-life commands, widening the scope of possibilities. This can sound very exciting, but unfortunately needs to be tempered a little bit. Indeed, EEGs are subject to numerous variabilities, such as the environmental condition, the subject's cognitive state, its fatigue, or the task requirement. Therefore, using a BCI requires frequent recalibration, hardening its use on a daily basis. In my PhD, I try to tackle those variabilities. For this, when I have an EEG, I convert it to its covariance matrix that gives insights on the connection of the different areas of the brain. Moreover, a covariance matrix has some interesting mathematical properties. It is symmetric, positive, definite, SPD. It therefore lives in the space of SPD matrices that can be endowed using a Riemannian metric leading to a curved space, a Riemannian manifold. It has been shown that when dealing with SPD matrices, leveraging this Riemannian geometry leads to better results when doing classification, for example. To be a little bit more precise on my work, I'm trying to build a probabilistic framework on the manifold of SPD matrices. For this, I take ideas from probability and statistics, mix them with tools from Riemannian geometry. By modeling a set of SPD matrices using a probabilities distribution that inherently accounts for this Riemannian geometry, I hope to better understand how variabilities impact datasets that come from real-life BCI experiments. For example, I could build a more informed classifier, but I could also reduce calibration time by transporting the knowledge learned on one subject onto another one using optimal transport, for example. I hope that my work helps us better understand and tackle variabilities that occur in BCI experiments, but also help people that are already equipped with BCIs better control them without needing constant recalibration. Thank you for your attention.
So please do not leave the stage. We want all the finalists to go on stage. We have a photographer, so I want some memories, and I'm sure that other people want to. So maybe a first picture without us and a picture with the three empty chairs. If you allow, we would like a picture with you.
So we'll conclude this session then. I wanted to say think deeply when making your choice. It's clearly a very, very difficult decision because all the presentations were very good. Must say that I presented myself Eusipco a few years ago, and clearly I wouldn't have competed at this level. It's a great level of presentations, and congratulations already for being in the 10 finalists. We'll have the results tomorrow, and the awards will be given in the gala dinner, so wait for there. And don't forget to give, of course, your votes at the end. I want to end thanking, well, all the jury, but especially Barbara for her efforts in making all of this possible.
Thank you very much. So do not forget to get back your voting sheets. The volunteers are waiting for them. And thank you, Julian.